Good morning, everybody. Welcome back to stellar pulsation theory. In yesterday's tutorials, Professor Yadav has discussed both the virial theorem and the mass-luminosity relation, and he has given a detailed derivation of both virial theorem and the mass-luminosity relation. Since both the virial theorem and the mass-luminosity relation are essential, very essential for our understanding of stellar evolution and stellar structure, I will comment on them today, or I will repeat some of the results he has derived yesterday, and I will discuss it in the framework of stellar evolution. How they are responsible for driving stellar evolution and what needs to be considered, what needs to be discussed in connection once these theorems are no longer valid. Okay, let's first turn to the virial theorem. Well, the virial theorem was derived on the basis of the equation of state of an ideal gas and the requirement of hydrostatic equilibrium. And we got the result that the gravitational energy is minus 2 times the thermal energy of the star. Well, the gravitational energy, the gravitational potential energy, is given by the integral over the mass of the gravitational energy per mass, which is gmr over r, and the integral over the mass gives the total gravitational potential energy of the star. The thermal energy, on the other hand, may be expressed by the integral over the heat content, which in this case is written by the specific heat at constant volume times the temperature. So this is the heat. This is the heat per mass and Kelvin. So this is the CV times T is the content, thermal energy content per mass integrated over the mass gives the total thermal energy content. If you compare it to Professor Yadav's notation, you will find a small difference, but if you rewrite the pressure over density, which occurs in his derivation, then you will end up also with the formulation that is CV, which is usually 3/2 times the gas constant. This is something like P over rho. This is what's remaining. So we are essentially ending up with identical formulations. So it's just another way of rewriting the thermal energy. Okay. Well, the assumptions to arrive at this form of the virial theorem was hydrostatic equilibrium. Now we are dealing with two kinds of energy, the gravitational energy and the thermal energy. So sometimes the virial theorem is confused with the energy conservation because we are dealing with energies. But we have not adopted the energy equation. What we have adopted is hydrostatic equilibrium. So keep in mind, the virial theorem has nothing to do with energy conservation, even if it uses in its arguments or in the result, it uses two kinds of energies. So it's just a consequence of hydrostatic equilibrium, has nothing to do with energy conservation. The second point is we have assumed the equation of state of an ideal gas. And actually, the ideal gas is responsible for the factor 2 here. If we take another equation of state, we will end up with another factor here. It's also in general, if you can derive the virial theorem, then in general you will get a similar relation, but the factor in front of the thermal energy will not be the same. For instance, if we take pure radiation, then we will end up with a factor of -1 here. So keep in mind, hydrostatic equilibrium, no no energy conservation is used, and we have used an equation of state of the ideal gas. So if we take another equation of state, we may end up with a similar form, but not with the factor of -2 here in front of the thermal energy. Okay, so virial theorem has nothing to do with energy conservations, and Professor Yadav already discussed the implications of the virial theorem in this form. Well, the first one is that the total energy, which is given by the sum of gravitational and thermal energy, is then given gravitational energy is -2 times the thermal energy is given by minus the thermal energy. Thermal energy is positive, so the total energy is negative, which means we have a gravitationally bound system. Well, then he considered, and I'm repeating this now because this is very, very important, and you have to go yourself possibly through this analysis again. Well, if we consider the contraction of the star, then we release gravitational energy. Why is that? Delta Eg is bigger than 0. Well, if we shrink our star, if we contract our star, the radius becomes smaller, so this becomes, the modulus of this quantity becomes bigger, and therefore the gravitational energy becomes more negative. So delta Eg is negative once the star contracts. So it releases then gravitational energy once we contract our star, and according to the virial theorem, then the change of thermal energy is -1/2 times the change of the gravitational energy, and once minus delta Eg is bigger than 0, delta E thermal is bigger than 0, so the star becomes hotter. The thermal energy increases. At the same time, we have that the change of total energy is minus the change of the thermal energy. That is equal to, of course, according to virial theorem, is equal to 1/2 times the gravitational energy. This is then negative. So we have we have the fact or the result that a decrease of the total energy is always associated with an increase of the thermal energy. So this is a system which loses energy, or once it loses energy, then it becomes hotter. This is very counterintuitive. All systems we know on Earth show the opposite. If they radiate energy away, if they lose energy, they become colder, they do not become hotter. So the total energy decreases. Decrease in total energy is associated with an increase of the thermal energy. This total energy, the decrease of total energy, of course, might be done simply by radiation of the star. And we saw once we went through this analysis, that half of the released gravitational energy goes into the radiation of the star, and the other half of the released energy is needed or used to make the star hotter, to increase the thermal energy. This is the result of the consideration we have had just before. So we have released the gravitational energy, half of it goes into thermal energy, and half of it goes into the total, goes into the radiation from the star. Okay, well, this question, or the association of increase of thermal energy associated with an energy loss from the total system, is usually addressed as a negative specific heat. We lose energy, and at the same time the star becomes hotter. Well, the question is, well, where does this come from? This is counterintuitive. This does not happen for any system we know except for stars. And there are other astronomical objects where this also takes place. So what is responsible? Where does it come from that a decrease of the total energy heats up the system? What is responsible? What do we usually not take into account, at least do not consider in the total system? It's gravity. So gravity is responsible for that strange behavior if we include it in our thermodynamic system. Of course, we could also regard the system only in a thermodynamic way. Then we would consider stellar matter as usual. But here we have explicitly taken into account gravity. And if we take both the thermodynamics and the gravity together, then we will end up with this strange behavior. So gravity, or the consideration of gravity, is the reason for this negative specific heat. I told you there are other astronomical systems where this exactly the same phenomenon happens. Gravity plays a major role. This is, for instance, in the dynamics of star clusters. If you consider a globular cluster and you take out, if you get rid of energy in the globular cluster, then it will shrink and the velocities of the stars become higher. This is nothing else but increasing the temperature of the star cluster. That means the thermal or the kinetic energy of the stars increase once you reduce, or once you get rid of, or you extract energy from such a globular cluster. So it has exactly the same properties. You take out energy of this globular cluster and the velocities of the stars will increase, or in other words, the counterpart of thermal energies is the kinetic energy of a star cluster. Then the thermal energy will increase in such a star cluster. So gravity is always responsible for this strange behavior that energy loss leads to an increase of temperatures or increase of kinetic energy in the case of a star cluster. Okay, so what we have, that loss of energy once the star lifts from its gravitational energy. So if it contracts, then the star lifts from this energy, is always correlated with an increase of the temperature during evolution. Actually, this is one of the driving factors for stellar evolution. This outcome of the virial theorem, or the implication of the virial theorem, that once the star loses energy, and of course it needs to live from its gravitational energy, so it contracts, it releases gravitational energy, then this will automatically lead to an increase of temperature. Okay, this is one of the basic phenomena or basic issues of stellar evolution. The second issue, which has been discussed yesterday, is the mass-luminosity relation. What has been used to derive this mass-luminosity relation is also hydrostatic equilibrium, as our stars are in mechanical equilibrium, and we have used the equation of energy transport, which connects the luminosity of the star with the temperature gradient of the star. It's simple diffusion approximation. In all diffusion approximation, or in all kinds, or in all situations where you transport energy by some kind of diffusion process, you relate a temperature gradient to the flux. The bigger the temperature gradient is, the bigger will be the heat flux. So the energy transport has been connected with a hydrostatic equilibrium, and together with an equation of state, we have, Professor Yadav has shown you that there is a relation between luminosity and mass. That means L, the luminosity, is fixed or determined by the mass only. There are no other parameters apart from opacity. Okay, there are minor effects, but from the main physical parameter of the star, there is only the mass left as a parameter of the luminosity. So the star's luminosity is completely determined by its mass. So if you have a star of a certain mass, you know it has to radiate it at the rate which is prescribed by the mass-luminosity relation. Once Professor Yadav has discussed the case when the equation of state is an ideal gas, and he has ended up with the relation between luminosity. Luminosity is proportional to the mass cubed. Well, this mass-luminosity relation also depends a little bit on, well, not the existence of the mass-luminosity relation. We always get a mass-luminosity relation, but the exponent by which luminosity depends on mass, this depends a little bit on the equation of state you use. So if you use as an equation of state, you take radiation pressure. Pressure is proportional to temperature to the fourth. You will end up with another luminosity mass relation, namely a linear relation between luminosity and mass. So if I may bother you with an additional exercise, simply take for exercise, take the pressure temperature relation P proportional to T to the fourth and redo or simply change a little bit the derivation you have seen yesterday given by Professor Yadav, then you will see you will end up with the luminosity, a linear luminosity mass relation in that case. So, well, these considerations are based on a very crude estimate. Very crude estimates. We have replaced differentials, simply dl by dm was replaced by L over m. This is a very, very crude way to estimate the to describe the properties of the system. So you may ask what happens to these relations once we do sophisticated stellar structure, solve stellar structure equation, do sophisticated stellar evolution theory. Well, the result is remarkably close to these relations. So what you find is if the stars have up to low mass or moderate mass, actually the luminosity is proportional to about mass cube. The exponent is very close to 3 for low mass stars. And actually, if you go to high mass stars, you find that the exponent reduces to 1. So even this case, where you assume that the star is mainly supported by radiation pressure, is also seen once you do sophisticated stellar models. This is valid, the exponent 1, or the linear relation, is valid for massive stars. The reason being, well, massive stars are more supported by radiation pressure than by gas pressure. So it's quite reasonable that massive stars being supported by radiation pressure show the linear relation between luminosity and mass, which is close to the linear relation, whereas low mass stars or intermediate mass stars show the mass cubed dependence of the luminosity. So it's remarkably close to the exact results that in principle one cannot expect it to work that nice, but of course it supports our point of view that we have done the right physics. At least we don't get the numbers quite right, not exactly right, but we get results which are very close to the real values. Okay. Well, the essential point is this relation, luminosity-mass relation, is valid irrespective of any energy generation process. And now we can come back to our initial question, why does a star radiate? Well, the star has to, once we fix its mass, it has to radiate at a rate which is given by the mass-luminosity relation. And what we have used is energy transport. So that means we have an energy flux because there is a temperature gradient. The energy transport relates the temperature gradient with the flux or the luminosity. And actually the luminosity is determined by the temperature gradient, or in other words, by the fact that the star is inside hotter than outside. There is a temperature gradient between the center and the surface, and therefore we have to have a flux. So the second question then would be, why do we have a higher temperature inside than outside? Well, and this is then controlled by hydrostatic equilibrium. Hydrostatic equilibrium tells you that gravity balances the pressure gradient, and if gravity has to balance, or the pressure gradient has to balance gravity, it's the other way around, then pressure gradient necessarily has to increase inward. This is a consequence of the hydrostatic equilibrium. Now, once you require the pressure to increase inward, if you have an ideal gas, then of course it could be done or could be provided by an increase of density. This actually is not sufficient. It needs, in addition, an increase of the temperature. So the pressure, the hydrostatic equilibrium, for the case of radiation pressure, it's immediately clear. You have a gradient of pressure. Pressure must be higher inside. If the pressure only depends on temperature, we have automatically a temperature gradient. Temperature has to rise from the surface to the center. In the case of ideal gases, you might argue that the density increase would be sufficient. It is actually not sufficient, and does also lead to an increase of the temperature. So the reason, or well, energy transport is energy transport in the form that temperature gradient and the luminosity have to be related together with the hydrostatic equilibrium, leads to this to the result that the star has to radiate at a rate which is given by mass luminosity relation. We haven't said anything about the energy generation, nothing. So the question, why does a star radiate? Well, we can answer this. This is simply due to the fact that the star is hotter inside than outside. It's like a cup of coffee. Cup of coffee is hot, so the hotter than its surroundings. Well, surroundings is usually cooler than the cup of coffee, so the cup of coffee will radiate because of its temperature difference with respect to its surroundings. The same is true for the star. The question then, of course, arises, how does the energy generation come into play here? The star has to radiate because it's hotter inside than outside. This is controlled by the transport and the hydrostatic equilibrium. And the question is how the second point, namely the energy generation, comes into play. Well, if the star has to radiate at a certain rate, then it has in some it's some kind of human phrasing. It has to look where to get this energy from. It has to see which energy sources are available to satisfy the prescribed luminosity. Luminosity is prescribed, and the star has to find an energy sources to satisfy or to fill in this luminosity at which it has to radiate. Well, the energy sources a star can use, well, one energy source would be it contracts, then it can release gravitational energy, and it can satisfy then the prescribed luminosity mass relation by simply using its gravitational energy and by shrinking or contracting. Then it might satisfy this luminosity mass relation. Or if it's possible, or if it's available, it can satisfy this relation by igniting nuclear burning, and can satisfy this luminosity mass relation by powering this luminosity by nuclear energy release. These are the two sources which are available for a star. Okay. Well, I've already said star has to radiate at a rate prescribed by the luminosity mass relation, and the energy production within the star has to adjust to provide the required luminosity. So it can do it either by gravitational energy, by contraction, or it can be done by igniting nuclear processes. Okay, second, well, If there are no nuclear energy sources, then the star has to rely on its gravitational energy. So if there are no nuclear processes are taking place, then it has to take its gravitational energy. So the star has to contract to release that gravitational energy and to feed the luminosity. As a consequence, then, if the star contracts, now the virial theorem comes into play. If the star contracts and releases energy, half of it goes into the luminosity, which it has to feed, and the other half is used to increase the thermal energy. This is a consequence of the virial theorem. Then the star has to become hotter once it leaves from its gravitational energy. So now we have the combination of these two phenomena, the mass-luminosity relation and the virial theorem. Well, what happens if the star becomes hotter? Then the temperature increase might lead to an ignition of the next nuclear burning stage. Yes?
So you explained that if the nuclear burning is not available, then the star has to rely on its gravitational energy.
Yes.
So this phenomena must be more dominant during the last stages of the star. Is it because when the star starts like dying, the nuclear fuel burns?
If this picture is correct until the end of the stellar evolution, then if it has arrived at the iron, iron is the nucleus with the highest binding energy per nucleon, then there is no fusion, no exothermic fusion possible. Then it would have to live from its gravitational energy, and it would become hotter and hotter and hotter. So what would I wanted to ask this question later on, but now I can ask it because you are. Now I can ask you the question because you asked the question. Well, what will happen then if this picture is correct, and we have arrived at an iron core in the center of our star? No nuclear processes are available. Even if we heat up the star arbitrarily, there is no exothermic reaction possible. So the star contracts, releases its energy. It still has to satisfy the luminosity mass relation. So how would we end up? What would be the pardon?
It will possibly contract and become more brighter or something like that. I mean,
well, the brightness will not change. Luminosity mass relation. Okay. Well, what would happen? Just simply describe the situation. It becomes hotter and hotter. There's a singularity in temperature. There, you cannot avoid a temperature singularity because the star has to radiate at this rate. It only has available the gravitational energy, so it shrinks and shrinks and shrinks, and the temperature goes to infinity. That's a strange situation, isn't it?
Yes.
Okay.
But should this be like this phase? Should this the question that you asked? Should this be analyzed using the hydrostatic equilibrium perspective?
Well, we have
in order to continue to be more in the equilibrium phase, it has to contract further, and whatever is radiated, something like that.
Yeah. Well, we have assumed, of course, hydrostatic equilibrium.
Yes.
This was the assumption. But given all these assumptions, we end up with a diverging temperature, if that's true. But let's stop perhaps at this situation and come back to this later on. Okay. May I ask you to wait for a few minutes and we come back to that question, because that is the question I wanted to ask at somewhat later stage. But it's good that you asked this question, but let me just explain some things before. Okay. Okay, so we have the situation then, how the stellar evolution will proceed. Well, there are two main ingredients. This is the virial theorem and the mass luminosity relation. So stellar evolution, according to what we have seen now, it proceeds in the following scheme. Well, if the star, let's start here at the left upper corner. Well, let's consider the star has had some burning phase and has powered its luminosity by nuclear reaction. So at some stage, the nuclear fuel will be exhausted, and it still has to power or satisfy his luminosity mass relation. So it has to take the energy, at least for some time, from the gravitational energy. So it has to release gravitational energy by contraction. Then it will become hotter according to virial theorem. The temperature will increase according to virial theorem. Well, the temperature increase then might lead to a temperature which is sufficient to ignite the next burning stage. You have seen the burning stages require successively higher temperatures. If we go from hydrogen burning to silicon burning, then the temperature increases because the Coulomb barrier of the reactions becomes higher and higher. So we ignite the next burning, and once the next burning is exhausted at some time, then the cycle goes on. Nuclear fuel is exhausted. The star releases again energy by contraction, then temperature increases to virial theorem, and so on. And this cycle continues for several times until, well, now we come to the question, what will be the final state of this evolution? Once we have reached iron as the ash of the last burning, then we would always go along this cycle, and we would end up with an infinite temperature as the final state of this evolution. Well, actually it doesn't take place, and what is the physical reason for this, for the fact that the cycle does not go on forever and we do not reach infinite temperature? Well, some of our assumptions seem to fail, and the assumption that fails is that the equation of state is no longer that of an ideal gas. So the virial theorem, keep in mind, was derived on the assumption that we have the equation of state of an ideal gas. So in the course of the evolution, this assumption will fail, and the virial theorem is in its form given by Professor Yadav will no longer be valid. So the virial theorem at some point of this kind of the evolution will no longer be valid. We cannot apply it anymore. And this actually virial theorem is responsible for an increase of temperature once the star contracts. So this is no longer valid because the equation of state changes. Okay, so to understand that, let us consider what happens to the temperature as a function of density. In the course of evolution, the density will increase because the star only shrinks. So the star contracts, so the density will increase with time anyway. This is a byproduct of stellar evolution. But what happens, the question is then, what happens to the temperature? Temperature, you would expect, if the virial theorem is valid, would also increase with time. But is that really true? Question. Okay, so we consider a homologous contraction of the star with time. Homologous means, this is an artificial construction, but it shows you in detail what really happens. Homologous means we keep the mass and the structure of the star constant. So the relative structure of the star is kept constant, and the quantities like density, pressure, temperature scale with the overall scaling factors. We keep, in addition, during evolution, this is not a bad assumption, we keep the mass of our star constant. Let's illustrate what that means, homologous contraction. Well, we write the density or take an estimate of the density with in the usual way. Density is mass over volume. The volume is proportional to r cubed for our star, so the density goes with mass over r cubed. If we differentiate this relation with time, and the time which we have in mind is now not the dynamical timescale, it's not the thermal timescale, it is the timescale of evolution, the timescale of contraction of the star. So the density changes by the change of radius. So if we take the density, the derivative of the density with respect to time, rho dot, and take the ratio of rho dot over rho, well, the mass is not changed, the mass is constant, then this is caused only by the change in radius. So we obtain rho dot over rho is -3, it's the exponent of this 1 over r cubed, -3 times r dot over r. It's simply differentiating this relation, keeping the mass constant. Well, we do the same for hydrostatic equilibrium, where hydrostatic equilibrium is estimated the usual way. We have hydrostatic equilibrium, dp by dmr is minus gmr over 4 pi times the radius to the fourth. Now we estimate it in a very crude way. This is pressure over mass is proportional to m over r to the fourth, or pressure is proportional to mass cubed over r to the fourth. Now we keep the mass fixed and calculate the relative change or the change of the pressure with mass along such a homologous contraction. What we end up with is p dot over p, like the rho dot over rho, is then given by -4, this is the exponent here, times r dot over r. Okay, so we have used definition of density, we have used hydrostatic equilibrium, our star will be in hydrostatic equilibrium, and finally what we need is the equation of state. The equation of state is written in the usual form. We differentiate the equation of state. Rho is a function of pressure and temperature, and if we differentiate this relation, then we have rho dot over rho is d log rho by d log p at constant temperature. This is our famous coefficient alpha times p dot over t minus our famous coefficient delta d log rho by d log t at constant pressure times t dot over t. Okay, what do we do now? We can replace the what we are doing. What we want to do is we want to calculate the t dot over t in terms of rho dot over rho. So what we are doing is we replace r dot over r by rho dot over rho and insert p dot over p is then 4 over 3 times rho dot over rho, and insert this here for p dot over p. So it's a simple relation. We eliminate r dot over r, then we have p dot over p as a function of rho dot over rho, and we insert the p dot over p as a function of rho dot over rho here. Then we get a relation between t dot over t as a function of rho dot over rho. Okay, everybody satisfied? Okay, so what we end up with is t dot over t is proportional to rho dot over rho, and getting all these dimensionless factors here correctly, we are then left with t dot over t is 4 alpha minus 3 over 3 delta. So how the temperature changes with time in relation to rho dot over rho. Rho dot over rho is positive because density increases, depends sensitively on the equation or on the coefficients of the equations of the equation of state, in particular on alpha and delta. Okay, now let's see what happens for an ideal gas? We are always starting with an ideal gas. So for an ideal gas, what is the value of alpha and delta? Okay. Pardon? It's alpha and delta are equal to 1 once we consider an ideal gas, and this is the configuration we are going to start with. We start stellar evolution with an ideal gas. In that case, virial theorem is valid, anything is fine. So alpha and delta equal to 1. What do we get for t dot over t as a function of rho dot over rho? We get 4 times 1, 4 minus 3 is 1 over 3. So it's 1/3 times rho dot over rho. Or if we integrate this equation, that means t goes with rho to 1/3. Okay, if we integrate this equation, then we have t dot over t is 1/3 times rho dot over rho, and that means the temperature increases with the power t with the power 1/3. Ideal gas, the temperature increases like the density to 1/3. Okay, now I have to remind you of a result which we had at the end of the discussion of the equation of state. We considered the transition, once we considered the equation of state, we considered the transition of the equation of state for an ideal gas to a degenerate electron gas. So we introduced there the condition for degeneracy to happen is that the thermal energy of the particles, this is of the order kT, so kT, Boltzmann constant times temperature, this is the thermal energy of a particle, is small compared to the maximum energy which is reached once we fill all our electrons into potential pot, and this is the maximum energy which is reached once all particles, all electrons are completely filled in the pot, in the potential pot up to a certain maximum. So this has to be smaller than the maximum energy or the Fermi energy E naught or E0, which is the maximum energy of an electron in the basic or in the ground state for all electrons. And then we defined on this basis the degree of degeneracy. Degree of a degeneracy would be the ratio of this energy to the thermal energy. This might be regarded as a degree of degeneracy. If this degree, this ratio is big, then we are closer to degeneracy. If this ratio becomes small, we are further off the state of degeneracy. So we may consider the ratio of K to kT over E naught or its inverse as a degree of degeneracy. Okay, so we have kT over E naught or its inverse is proportional to what we defined of degree of degeneracy. If we want to keep this degree of degeneracy constant, then the temperature has to be proportional to E0. So constant degeneracy would mean constant degree of degeneracy would mean that the temperature is proportional or goes with the maximum energy of or the Fermi energy of our particles. Now, how does this maximum energy depend on the momentum? Let's assume for the moment these are non-relativistic particles. Then the energy is proportional to P naught squared over 2m. So in that case, we have P naught squared over 2m. The m is not interesting for us, so we drop it here. The P naught depends on the number density of our electrons. Do we remember what is the dependence of the maximum momentum on the number density of our electrons? If we have a lot of electrons, we have, of course, we have to fill it to a higher momentum or a higher energy than in the case when we have small small number of electrons. Does anybody remember what we got there? Well, this P naught goes like number density of electrons to 1/3. Okay, so we have that this quantity goes like the number density of electrons to 2/3, because this has power 2. So if we have charge neutrality, then for each electron we have a nucleon. So this will be proportional to the density of our matter. So in that case, we would get T is proportional to the density to 2/3. So if we want to keep the degree of degeneracy constant, then the temperature has to rise with the density at least for constant degree of degeneracy exactly with rho to 2/3. If we want to stay in a non-degenerate state, then the temperature has to rise faster than rho to 2/3. Okay, so now we consider these two two cases. Well, for an ideal gas, we have that the temperature goes with rho to 1/3, and for constant degree of degeneracy, we would have the temperature to rise with rho to 2/3. So it has to rise faster than the temperature rises in the case of an ideal gas. What does it mean? Well, the degree of degeneracy, once we have an ideal gas and the star evolves, does not stay constant, but the degree of degeneracy increases, or the matter within the star becomes more and more degenerate. And finally, the final state, if it goes on, then the final state will be a state where the equation of state will be controlled by that of a degenerate electron gas. So we enter successively, we enter the domain of degeneracy, and finally we will end up with an equation of state of that of the first non-relativistic degenerate electrons. Okay, well, what does it mean for the alphas and delta? Well, for non-relativistic electron gas, which will be the final state here, delta is 0. Well, we have P proportional to rho 5. Degeneracy means the pressure does only depend on density, and temperature drops out as a parameter. So the pressure goes like rho to 5/3 for a non-relativistic degenerate electron gas. So the alpha, which is d log rho by d log p, is 3/5 for non-relativistic electrons, and the temperature drops out as a parameter, so the derivative of the density with respect to temperature is 0. So once initially we have an ideal gas with alpha equals 1, alpha equals delta equals 1. Sorry, I don't get it on the same transparency. So we start with alpha equals delta equals 1. A temperature increase like rho to 1/3, enter the domain of degeneracy for electron gas. Then alpha varies from 1, this is the case of ideal gas, to 3/5, and delta varies from 1 to 0. What happens with our temperature, the change of temperature with respect to the change of the density? Well, what we see here, it's 1/3, this factor is 1/3 for the ideal gas. Now let's have a look what happens. The nominator will change sign at which value of alpha? Alpha equals 3/4, then T dot over T is 0. So we have a change of sign. Usually we have an increase of temperature with density, but this may change the sign once alpha is 3/4, and we have seen alpha changes from 1 to 3/5, so it passes the position 3/4, so it becomes smaller, and this leads to the fact that T dot over T becomes negative, so that the temperature decreases with increasing density. And this means we have a maximum temperature once we have a transition from an ideal gas to a degenerate electron gas. Moreover, the delta goes to 0, so this will be a very steep dependence. Once we go to delta close to 0, then the temperature will decrease, but it will decrease with a very steep slope because delta goes to 0. So keep in mind, for alpha bigger than 3/4, we have an increase of temperature with density, and for alpha smaller than 3/4, we have a decrease. And that means we necessarily get, by this transition from an ideal gas to a degenerate gas, we automatically get a maximum in temperature. Temperature at some stage, once we reach degeneracy, will decrease with density. Okay? Okay, we have T dot over T bigger than 0 for alpha bigger than 3/4, and T dot over T smaller than 0 for alpha smaller than 3/4. Well, so in the case of degeneracy, the temperature decreases for contraction, and it means it achieves a maximum, and then the temperature is can no longer become higher than this maximum. And as a consequence, if there is a temperature maximum and we are just in a stage between two possible burning phases, that means that the next burning stage possibly is not reached, and you cannot go through the next burning stage. Well, this helps with our strange situation which came up once we asked what happens if the virial theorem would be valid forever. Then we would get an infinite temperature. This is prevented here by the fact that the gas or that the stellar matter becomes degenerate. So this quantum mechanic effect of degeneracy really influences on a macroscopic way. Degeneracy is usually thought to be a microscopic effect. Here it has macroscopic consequences, because this quantum mechanic effect of degeneracy prevents the star from getting infinite temperature. It prevents, or it is responsible for the fact that all stars, more or less, all stars have, or at least some stars, I will comment on it in a minute, that some stars will reach a maximum temperature and may only undergo several burning stages, and the later burning stages cannot be achieved because the temperature maximum is reached before the next burning stage would be ignited. Okay. So the higher burning stages will not be burning phases will not be reached if degeneracy sets in before that. Okay, the next consequence is there is a maximum temperature or maximum temperature during contraction and transition from the ideal gas to a degenerate electron gas. So the question arises, where does this temperature maximum actually, where the temperature maximum actually is achieved, and on which parameter this temperature maximum or the reaching of the temperature maximum is controlled. And here I have to, I cannot demonstrate this because this requires real stellar evolution calculations, but in a schematic way it looks like the following. So this is, in a schematic way, the run of the temperature with density. Here we have log central temperature against log central density, and the thick arrows are the tracks or are the lines along which the star evolves during stellar evolution. So if the mass is small, then this maximum occurs at a finite density. Temperature increases, then alpha becomes equal to 3/4. Then we have reached a maximum, and then we have a decrease in temperature. So we reach a maximum in temperature. If the mass is smaller, then this maximum is reached earlier. So for masses smaller than 0.1 solar masses, it's reached, in particular here, before a temperature of 10 to 7 K is reached. What does it mean for 0.1 solar mass star? If this maximum due to the transition to degeneracy is reached before a temperature of 10 to 7 is achieved, this maximum occurs below temperature of 10 to 7 K. What is 10 to 7 K? Is this a which nuclear fusion? It's hydrogen. Hydrogen fusion occurs around 1 times 10 to 7. So a star with mass smaller than 0.1 solar mass will not reach hydrogen burning. Well, it has to be bigger to reach hydrogen burning. Well, and then the next gap, or the next domain or region of masses might not, if the mass is not massive enough to get a temperature of 10 to 8 degrees, it will not ignite helium. If it's more massive, then it might ignite helium, but not yet carbon. And so, well, you have a range of masses, and depending on the mass, you will not reach either helium burning, even not hydrogen burning, even not helium burning, or carbon burning, oxygen burning, neon magnesium burning, and you will stop the evolution due to degeneracy before some of these stages of burning are reached. Okay, this is an effect of degeneracy. Well, for very massive stars, here we have the 10 solar mass star, well, this does not reach degeneracy, or it reaches degeneracy after silicon burning. In any case, it will reach degeneracy once it has done once it has undergone silicon burning, because this is the last burning stage. Then the star has to contract, and once it contracts, it enters always the degeneracy regime. But this is no longer telling you whether the next burning stage is reached or not, because we have already undergone all the exothermic burning stages. So even in the case of a very massive star, we will in the end up with a degenerate iron core. This would be a star which is massive enough to undergo all the burning stages. If it's less massive, then the evolution may stop before silicon burning, or if the star is even less massive, then it will stop before oxygen burning, or even if it's very low mass, then it even stops before it reaches. It even stops before it comes to hydrogen burning. This is the case for masses below 0.1 solar mass. Okay, that's the evolution in a schematic way in the interior of a star. So which stages of burning are reached depends on mass, and the final stages of stellar evolution will then will either be degenerate stars. So it's always, degeneracy is always the final stage, or we end up with stars which have degenerate cores. Degenerate iron core, or the complete star, except for its envelope, is degenerate. These are the final stages of stellar evolution, and in that way, degeneracy avoids this singularity in the temperature which would be present once the virial theorem would be valid until the end of stellar evolution. So degeneracy, a quantum mechanical effect, is essential for stellar evolution. Okay. So in the end, what this tells us is we have to deal with degenerate stars, because that seems to be the only way a star can end its life. So let's go to the property of degenerate stars. Well, the equation of state of a degenerate gas is depending only on density. So we have a function of the pressure is then no longer a function of temperature. It is it is only a function of density. Now let's estimate in the usual, or shall I stop here? Okay, then let's have a break and we continue after that. It's a good place to make a break because now we are considering degenerate stars. Now we've seen stellar evolution usually ends up with a degenerate star. Either the core of the star is degenerate or the entire star of the will be degenerate. That means the equation of state, this is one expression of degeneracy, does no longer depend on temperature, and we have a direct pressure density relation. Okay, once we have a pressure density relation, what does it mean? Well, we go the usual way, we estimate our differential equations. Then pressure, the hydrostatic equilibrium, which is of course also valid for degenerate stars. Pressure gradient has to balance gravity. In the Lagrangian form, dp by dmr is given by minus gm over r to the fourth, and we estimate this relation in the usual crude way. We replace the pressure gradient by p over m, and the right hand side will be then proportional to m over r to the fourth. So the pressure goes with mass squared divided by the radius to the fourth. Now, if we have, well, of course, the density is also estimated in the usual way. The density is given by the mass over the volume, or mass over r cubed. Well, what does it mean if we have a pressure density relation? Then the pressure may be expressed in terms of m over r cubed, and then we have a relation from the hydrostatic equilibrium, well, which also depends on the mass and the radius. So what do we end up with? With a relation between mass and radius. So typical for degenerate equation of state is that we end up with a mass-radius relation. By assuming hydrostatic equilibrium, then we express the pressure in terms of mass and radius. Pressure density relation gives us a relation between pressure mass over r cubed, and therefore we have the only parameters left in the relation is mass and radius, and we are left with a mass-radius relation. So if we assume the equation of state for non-relativistic fermions, for instance non-relativistic electrons, then we have seen that the pressure goes with a density to 5/3, and once we insert this relation into our pressure mass radius relation, density mass radius relation, it's perhaps nice if you do it as an exercise. Simply take these relations, assume a pressure density relation of that form, and you will end up with a mass radius relation. Do you remember the mass radius relation you have seen yesterday in Professor Yadav's pun? Yes, the radius goes for a normal star goes with m2, well, roughly 1. The radius increases with mass. What we see here, what does the radius do with mass? For a degenerate star, it decreases with mass. So if we put mass on a degenerate star, which is described by this equation of state, then the radius will decrease once we add mass to it. Well, what will be the consequence once we decrease? Well, I have to say there are of course stars which satisfy this mass-radius relation and which are very nicely described by the equation of state of a non-relativistic degenerate gas. They obey this mass-radius relation. These are the white dwarfs. You probably, all of you who have studied a little bit of astrophysics came across the white dwarfs. These are degenerate stars, and the mass-radius relation is R proportional to mass to minus 1/3. Okay, now once this is the mass-radius relation for non-relativistic fermions, we may ask what will be the mass-radius relation for relativistic fermions. Relativistic fermions would be those characterized by an equation of state where the pressure goes with a density to 1/3. So let's take this pressure density relation and ask what is the mass radius relation. Well, what we end up with, the mass has to be a constant here. So if the equation of state is given by relativistic electrons, then the mass radius relation will no longer be a relation between the radius and mass, because the radius cancels. You can convince yourself simply by inserting this relation, and you will find radius is no longer a parameter of the relation, but the mass is actually a constant. What does it mean? If we have a configuration or a star which is characterized by this equation of state, it means there is only a single mass possible. What happens if the mass is smaller than this value? Well, if it's smaller than this value, then gravity will be smaller than in the case of this constant mass given here. So gravity will be smaller, and pressure will push it back to a region where possibly, well, we come to this in a moment, we'll push it back so the star will expand. If the mass is bigger than this value, then the gravity will always be bigger than the pressure gradient, and the star will collapse. So there is a single mass which is possible for equilibrium. Any other mass will not be in equilibrium. Okay? There is a constant mass which is determined by the constants which are appearing in the equation of state and in the equation for hydrostatic equilibrium. Here the radius is a function of mass, and it shrinks once the mass is increased, and here we have only one equilibrium configuration which needs to have a very well specified mass. If the mass is smaller, the star will be expanding, no equilibrium possible. If the mass is bigger, then the star will contract. Okay, this constant mass, or this unique mass, is called Chandrasekhar's mass, and it's it has been found, or it has been defined the first time by Chandrasekhar, who considered in detail all these degenerate stars. Actually, I have to perhaps add a historical remark, because Chandrasekhar was considering the case or the possibility that stars might be described by a degenerate equation of state. And those days he worked together, or he was a student of Eddington in Cambridge, and Eddington strongly objected against his ideas. Even the sad thing about this, it was even a personal offense against Chandrasekhar. Eddington did those time, and Eddington never believed what Chandrasekhar did, but the case or the consideration of degenerate equations of state is essential for stellar physics. Now, well, Chandrasekhar got a Nobel Prize much later than his discovery. So it's now recognized, of course, that he was right, Eddington was wrong. But he must have had a very hard time together with Eddington, because Eddington was obviously not very nice to him. So you see, without degeneracy, we would not be able to stop stellar evolution. We would get an infinite temperature. That was the case before. So if degeneracy would not be there, we would have an entirely different stellar evolution. And Chandrasekhar, in a natural way, explained the mass-radius relation for white dwarfs. So he described this correctly, and he invented, or he gave this limiting or unique mass, which is obtained once pressure goes to with density to 4/3 for the relativistic fermions. So what is the meaning of this constant mass, and what is the meaning of Chandrasekhar's limit? Now consider a sequence of white dwarfs. Let's have a sequence of white dwarfs and let's increase the mass. Once we increase the mass, well, the density would increase if the even if the radius would be constant, but the radius decreases with mass, with minus 1/3. So in any case, mass increase leads to the increase of the density. Well, this implies that also the number densities of the electrons increases. Of course, charge neutrality would require that also the number density of electrons would increase. That means number density of electrons is proportional to, if in terms of the Fermi momentum, the maximum momentum in the distribution of our electrons, once it's completely degenerate, we have P naught squared is proportional, P naught is proportional to number density of electrons to 1/3. Okay, so this means that the Fermi momentum will increase due to the increase of the number density, so Fermi momentum goes up, and then of course also the energy of the particles will increase. Energy, the maximum energy for relativistical particles is proportional to P naught squared over 2m. So if we have an increase of the Fermi momentum, also the energy of the particle will increase. So if this process goes on for a sufficient time, well, we will have then an increase of the energy until the relativistic domain is reached. Here we have the classical non-relativistic particles, and once we increase the mass and the epsilon goes up, then ultimately we will reach the state where epsilon becomes relativistic, or the energy has to be considered to be relativistic energy, and therefore the electrons will become relativistic. So we have, with increasing mass, we have a transition from non-relativistic to relativistic degeneracy, and therefore a transition from an equation of state going proportional to rho to 5/3 to the equation of state where the pressure increases with rho to 4/3. Well, if we end up with relativistic degeneracy, we know that this requires, or there's only one mass for which equilibrium can be maintained. Okay, if this mass is smaller than Chandrasekhar's limit, what will happen? The star will expand and it will come back to a less dense region, so it comes back to the non-relativistic region. So if we end up piling up material, if we end up with a mass which is equal to Chandrasekhar's limit or a little bit above, then the star will collapse. So this is actually the maximum mass for white dwarfs. If we add mass onto a white dwarf and we make this thought experiment, then the Fermi momentum, the number densities of electrons will increase, the Fermi momentum will increase, the energy will increase until the electrons become relativistic, and then we enter the domain of relativistically degenerate electrons, and therefore we have only one particular mass for which we can have equilibrium. If the mass is smaller, it goes back to the non-relativistic regime because it expands. If the mass is just the Chandrasekhar's limit or a little bit above, it will collapse. So, and this gives rise to a very well-known phenomenon in astrophysics. This is the cause or the onset of so-called supernova explosions. Actually, this thought experiment is done in a scenario which leads to supernova explosion. For instance, if our white dwarf is in a binary system and the companion sheds mass on the white dwarf, then it increases its mass. This is actually the process which is found in binaries. The companion sheds mass on the white dwarf, thereby its mass increases, and thereby the white dwarf finally reaches Chandrasekhar's limit. What happens then is a collapse, and the consequence is a supernova of type 1a. These supernova of type 1a are nice candles in the universe because their initial condition, essentially the initial condition, is the same for all of these processes. There's just one single mass which can be at the onset of this collapse. And therefore, these supernovae of type 1a are thought to run all in the same way, because the mass is, this unique mass is always the same. The initial conditions are the same, and therefore also the following evolution of the supernova 1a explosion should be similar. And that means their maximum brightness should be the same, and so they can be used as for standard candles. Once the brightness of them can be assumed to be the same, we can use that in different distances, and then by comparison again with the apparent luminosity of the supernova of type 1, we can determine the distance. So the supernovae of type 1 are standard candles for the measurement of distances. The reason for them to be standard candles, or the main reason for them to be standard candles, is that the initial mass before collapse is Chandrasekhar's mass. Question: why do they explode? Well, there have been white dwarfs onto which material has been put. Well, white dwarfs are the leftovers from stellar evolution. Well, these might be white dwarfs which contain carbon and oxygen, because carbon and oxygen burning has not been reached. So the interior of these white dwarfs may consist of carbon and oxygen. There are helium white dwarfs, these are white dwarfs which have ended their life, or which have become degenerate before carbon burning, before helium burning is ignited. So there is a variety of white dwarfs: helium white dwarfs, carbon oxygen white dwarfs, neon magnesium white dwarfs, and so on. So what happens is, well, if the star collapses, it's a degenerate star which collapses, then there is still nuclear fuel left which could be burned, because we have not yet reached the iron stage. So there is binding energy per nucleon left. So the remaining helium, carbon, oxygen, neon, magnesium can be ignited, and therefore this could release nuclear energy. This is done under degenerate conditions. Degenerate conditions, I will not go into the detail, means that there is a runaway, a thermonuclear runaway, because the temperature does not react on, or the star does not react on a temperature increase, because the pressure is made up by the electrons. Pressure is, during this collapse of the white dwarf, is maintained by the pressure of degenerate electrons. Now the nuclei are compressed, temperature goes up, and they will start to ignite, helium burning, carbon oxygen burning under degenerate conditions. But the star will not react on the temperature increase, because the pressure does not feel the temperature, the electrons maintain the pressure. That means that the released energy will enhance the temperature even more, and we get a thermonuclear explosion or thermonuclear runaway. So the end of the evolution will be a total disruption of the star. Supernova of type 1a are thermonuclear explosions initiated by collapse, starting with Chandrasekhar's mass. The star is disrupted by nuclear explosion. So this is one of the scenarios by which a star can end its life. That's where the degeneracy of the degeneracy comes in. Another scenario which has to do with the degenerate core is the supernova explosion, supernova of type 2. What we are talking about, we are supernova of type 1a in a binary system, thermonuclear explosions. They still have unburned nuclear fuel left. This is not true once a star has reached silicon burning and leaves behind an iron core. There is no nuclear fuel left because the iron has the highest binding energy per nucleon. In that case, once the nucleus of a massive star, the star has to have more than about 10 solar masses initially, then we will end up with a degenerate iron core. This degenerate iron core becomes bigger because silicon burning on top of the iron core will lead to an increase of the mass of the iron core. So the silicon burning results in iron group elements as the ash, and the ash will become bigger and bigger, and so the mass, similar to the white dwarfs, on which the mass is shed by a companion, the mass of the iron core within a massive star will increase and then ultimately reach Chandrasekhar's mass and collapse in the same way. So the essential process reaching Chandrasekhar's mass is the same both for supernova of type 1 and type 2, but in one case it's caused by a companion shedding mass on the white dwarf. For very massive stars, it's simply the increase of the iron core by the superimposed silicon burning shell, which adds mass to the iron core. Well, what happens then? There is obviously no nuclear fuel left. It cannot burn exothermically. It forms finally during the collapse. It forms a neutron star. The envelope falls down onto the neutron star and is repelled, and then by a shock wave, the entire envelope is expelled and a neutron star is left behind. So in any of these two processes, the Chandrasekhar's mass plays an important and the decisive role here. Okay, so this process, both in very massive stars forming iron cores, or in binaries where where white dwarfs get mass from their companion, Chandrasekhar's mass plays a decisive role. Okay, this is the basis of supernova collapse and explosion. Did I forget something? No. Okay. Okay. So finally, this should close our digression into stellar evolution. Essentially, I have left one chapter on semi-analytical stellar models. That is done because we will resort to these models also in considering stellar pulsations. We will use them as toy or idealized models to study stellar pulsations. These are the polytropes. And how much time do I have? 5 minutes. So let me just introduce what polytropes are. Polytropes are stellar models which are based on the assumption that pressure only depends on density. And in a particular form, well, pressure depends on density in the form of a power law. Pressure is given by a constant times rho to some power, and the power is usually written in terms of 1 plus 1 over n, where n is called the polytropic index. So it's very similar to what we considered before for the case of degenerate non-relativistic and relativistically degenerate stars. It is the construction of a stellar model with prescribed pressure-density relation. It does not mean that the pressure-density relation, or does not mean that the equation of state has to have this form. This pressure-density relation may be caused also by a particular way in which energy is transported, plus the equation of state. We'll see that in a moment. So it's a formal way to describe pressure-density relation without any reference to the temperature. It's a formal way to close the system of equation. What we do once we assume a pressure-density relation, what is achieved then? What about energy transport? What about energy equation? You will get rid of that, because once we assume that pressure and density are related, we decouple the thermal equation from the mechanical equations, and we, so to say, we close the system of the mechanical equations by assuming this polytropic relation. So far it's just a formal relation, and the question is, when is this relation justified? Well, one justification would be the case we discussed a few minutes ago, if the equation of state is itself containing a pressure-density relation, for instance in the case of degenerate electrons, relativistically or non-relativistically degenerate electrons. This is one case which is covered by this formal relation between pressure and density. Another way to realize such a relation would be if the energy transport would be very efficient. Very efficient energy transport would mean temperature is constant. This is not met in stellar environments, but let's assume we have an extremely efficient energy transport, then the final state will be temperature is constant, and we have, once we have an equation of state for an ideal gas, then we would have P is proportional to rho times T. If T is constant, then P, the pressure, would be a function of the density only. Another way of obtaining such a relation between pressure and density would be to assume that the nabla, that the logarithmic logarithmic derivative of temperature with respect to pressure is equal to the adiabatic value. Nabla, keep in mind, is the value of d log T by d log P, which is actually achieved in the star. To define this, you need to have a temperature stratification, a pressure stratification. You have to compare them to derive or to define the nabla. So this is based on a real stellar model, or needs a stellar model to be defined, and nabla adiabatic is determined on the basis of thermodynamics only. You don't need to refer to a stellar model to determine nabla adiabatic. What happens then? Efficient convection. We discussed that. If the convection transports energy efficiently, then we know then nabla will be close to the adiabatic value. Or in other words, that within the star we have a constant entropy. Nabla equal to a nabla adiabatic means that the entropy is constant. Once we write pressure as a function of density and entropy, then this means entropy is constant, and we are left with a relation between pressure and density alone. So in any of these cases, we end up with a pressure-density relation. Keep in mind, it's not necessarily that the equation of state gives a pressure-density relation, but energy transport together with the equation of state may also give a formal relation between pressure and density. So there are applications of this polytropic relation to stellar models. Okay, so well, one question: where is this condition met? Do you remember? Pardon? No, this condition. Which stars can be described by nabla equal to nabla adiabatic? I've mentioned it probably only very shortly. Once we consider the Hertzsprung-Russell diagram, there is some imaginary line on the right-hand side. This is this the Hayashi track, and actually you can calculate the Hayashi track by calculating models which are described by nabla equals to nabla adiabatic. So we can use polytropic theory to define the Hayashi line at the right-hand border in the Hertzsprung-Russell diagram. So this has actually applications. For instance, the Hayashi line would be an application of the polytropic theory. Okay, so we have introduced this formal relation between pressure and density. And we have justified why we should or why we could describe at least some situations by this pressure-density relation. In some sense, both equation of state and the thermodynamics energy transport are, so to say, condensed in a pressure-density relation. So we assume that we can replace the thermodynamics simply by this formal pressure-density relation. And the question now is, what is the consequence? How can we solve the equations, and how do the solutions look like? So we will continue this afternoon. Good afternoon. Okay. Good afternoon, everybody. Welcome back to the theory of stellar pulsations. This morning we have considered some simple stellar models. Simple stellar models means we have closed the equations by assuming a relation between pressure and density in a rather formal way. That means we have assumed that the pressure is proportional to the density to some power 1 plus 1 over n times a constant k. And the index n is called the polytropic index. This relation is given by in a formal way and needs some justification, in which case a relation between pressure and the density may be assumed as a formal condition for closing or for having a closure of the mechanical equations. So what we are doing is we're trying to solve the mechanical equation, meaning we solve the mass conservation and the equilibrium equation, asking for an equilibrium solution of the mechanical equation, and justify that the pressure and density is given by a relation similar to a polytropic prescription. Well, one justification of this relation would be that we have an equation of state which itself provides a relation between pressure and density. For instance, the general electrons will result in a relation between pressure and density. Another way or another justification for a polytropic relation would be if the energy transport is very efficient. For instance, if the energy transport is so efficient that we may assume that the temperature is constant, then if we have an ideal gas equation as the equation of state, then the temperature, there will be a relation between pressure and density. Another case which may result in a pressure-density relation is if the convection is efficient. This happens, for instance, at the very for cool stars or for cool region within the Hertzsprung-Russell diagram. For instance, on the Hayashi line, the Hayashi line is considered, or the definition of the Hayashi line involves that the relation that the value of nabla is equal to the adiabatic value. This means convective is very efficient. Then the stellar models along the Hayashi line will lead to a pressure, an equation of state where pressure depends on density and entropy. Once the entropy is constant, because nabla is equal to nabla adiabatic, this means the pressure is a function of density. So the thermodynamics of such stellar models is condensed in a pressure-density relation, and this pressure-density relation is given in the form of a power law as a function of density. So the pressure is a power law in terms of the density. Okay, so what kind of solutions or what kind of models do we obtain once we use or once we assume a power law of in terms of the density of the pressure dependent on density? Well, what we have to solve is the equation of hydrostatic equilibrium. 1 over the density times the gradient of the pressure is the gradient of the gravitational potential. And the gravitational potential itself, of course, has to satisfy Poisson's law. That means the plus operator acting on the potential is equal to 4 pi times the gravitational constant times density, pressure, and the potential, and we have two equations. So we have we need one more equation to close this system, and the system is simply closed by the relation between pressure and density. So this the closure of the mechanical equation, Poisson's equation for the potential and hydrostatic equilibrium, is closed by the relation between pressure and density. So this is the so-called the equation for the so-called polytropes as a sort of stellar models. So we obtain stellar models where the pressure-density relation is prescribed by a power law of the pressure depending on the density. Okay, so we first introduce, of course, spherical symmetry. Our star is spherically symmetric, so the radial version of the gradient of the pressure and the gradient of the potential is given by 1 over rho. Gradient of the pressure is given by minus the gradient of the potential, and the spherically symmetric version of the Poisson's equation results in 1 over r squared times d by the r of r squared d phi by the r. This is the radially symmetric of Poisson, for the Laplace operator is equal to 4 pi g rho. Now, once we insert equation 1 into equation 2, that means we replace the gradient or the derivative of the potential with respect to r in the second equation, we eliminate the potential simply by inserting the d phi by the r into the second equation. Then we have an equation which depends on the density and the pressure gradient. Now we insert the polytropic relation. We replace the pressure by a power law in terms of the density, and then we end up inserting 1 into 2 and replacing the power law in terms of the density of the pressure. Then we are left with the following equation. This k comes from the polytropic relation. There's one derivative to be taken from the pressure, and what is left is the pressure in terms of the power law in terms of the density times d rho by the r. So this is simply the Laplacian operator acting on the pressure is equal to 4 pi times g times the density. So what we end up with is a second order equation of for the density stratification of our stellar model. Okay, this is simply a combination of hydrostatic equilibrium, Laplace equation, and introducing the power law for the polytropic dependence of pressure and density. Okay, to get the conventional standard form of this equation for the density, second order equation of the density for the to get into the usual or the common formulation of this equation, we normalize or we transform the density to a new variable. The new variable is the quantity theta, and we write the density in terms of the central density. So we normalize the density with the central value times a function theta to the power n. So this is our new variable, theta to the power n, and the normalization of the density that is done with the central density. Moreover, we introduce a new radial variable by taking a dimensionless variable psi and the normalization constant alpha. Well, the normalization is obtained by choosing a particular value of alpha such that this psi is a dimensionless quantity, and alpha is depending on the constant we have in our original equation by the constant k, which comes from the polytropic relation, which comes also from the 4 pi g, which is the gravitational constant, and from the central density. If we take alpha equal to this combination of constants, central density, and the polytropic index, then we obtain a dimensionless quantity psi, which is normalized, or which leads to a normalization of the radial coordinate r. R is then given by alpha, which gives the radius in physical units times a dimensionless unit psi. Okay, so if we do a normalization and transformation in this way, then the equation becomes rather simple, or simpler than before. Well, we have a Laplacian operator, the radial part of the Laplacian operator, which looks similar like the original Laplacian operator in terms of radius. Now it's in terms of the dimensionless quantity psi. It's 1 over psi squared times the derivative with respect to psi times psi squared times d theta by d psi. So this is simply the Laplacian in terms of the transformed variable theta and the transformed variable psi. So theta is a dimensionless unit, it's a dimensionless quantity, and psi as well. And on the right hand side, we are left with essentially with the density. This is this term here, and so we have, when density is normalized by the central density, we have on the right hand side, we have minus theta to the power n. So this is a dimensionless equation for the quantity theta and the independent variable psi. And it was first time it was given by Lane and Emden, so this is famous Lane-Emden equation for the structure of a polytropic star. So what this equation describes is the structure of a stellar equilibrium, stellar mechanical equilibrium, where the pressure is given by a polytropic relation on the density. Okay, so the question is, what is the solution of this equation? Well, let me see. Well, we have to have, of course, this is a differential equation, and the differential equation needs some either boundary conditions or initial conditions. Well, one of the initial conditions is that theta at the center of our object, this will be the center of the density of the star, and the density of the transformed variable for the density. Well, we have normalized the density by the central value, so the initial conditions for integration would then be that theta is equal 1. If we normalize the density to the central value, that means theta is 1 at the very center of the stellar model. Well, the second condition then is that of course we would like to have non-single solution. So when we will come to we will later on discuss the so-called singular points of differential equations. We will arrive at the discussion the discussion of singular points. What is a singular point of the equation? Well, let us write down the Laplace operator. Then we will have the first is d2 theta by the psi squared, and if we do the differentiation, this gives plus 2 over psi times d theta by the psi is equal to minus theta to the power n. So there is 1 over psi. Psi is the radial variable. Now, if we rewrite or multiply it by psi, we get a nicer version of this equation. So psi times d2 of theta by the psi squared plus 2 times the theta over the psi is equal to minus psi times theta to the power n. Now, what we would like to have is a non-singular solution for theta. Otherwise, we cannot interpret the density. Once we get a point where the highest derivative, where the coefficient of the highest derivative vanishes, is a so-called singular point, which means we do have, apart from regular solutions which do not diverge, we have also solutions which diverge at a singular point. So we have to exclude those solutions which have a singularity which diverge at psi equals to 0. Well, psi equal to 0, that's where the coefficient of the highest derivative vanishes. And so if we want to have a finite solution, then the second derivative of the variable theta should not diverge, should not become infinite, and also the theta, the variable theta, should not become infinite. That means if they remain finite, both the second derivative of theta and theta itself, then of course a consequence would be that the theta by the psi has to be 0 or has to vanish at psi equal to 0. Psi equal to 0 and finite second derivative and finite function theta, then this would imply that the derivative of theta with respect to psi has to be 0 in the center of the stellar model. So for regularity, for a regular solution of the Lane-Emden equation, we would require that the derivative of theta with respect to psi should vanish at the center. So we have two boundary conditions for this equation, the equation of second order with two initial conditions or two boundary conditions. One is that theta at psi equal to 0 should be unity, and for regularity reason, the derivative of the function theta at this center should vanish. So we have two boundary conditions, and we can the conditions, or we have enough conditions to solve this equation. The equation must be solved together with these two initial conditions. So we have an initial problem to be solved and to provide a function theta which denotes or which represents the density structure of the polytrope. Actually, once we consider n equals 0, we obtain an analytical solution. An analytical solution is also obtained once the polytropic index is 1, and also for polytropic index n equals 5, we obtain an analytical solution. Why is that? Well, take n equal to 0, then we have unity on the right hand side, and we have a linear equation of second order. This has an analytical solution, and also this is true if n is equal to 1, then the right hand side is a linear equation. We have a linear differential equation which we can solve analytically. I will not go into the details and won't derive or discuss these analytical solutions for some finite value of the variable psi. Well, I also have some plot for the solution looks like the following. So we have here the on the x-axis we have the variable psi, and on the y-axis we have the function theta. So the initial condition for the integration of Lane-Emden's equation is that theta is 1 in the center, and it starts with an horizontal tangent, so with d theta equal to d theta by d psi equal to 0. So this is where the integration starts. Once we integrate for a particular value of the polytropic index, then we will reach a 0 depending on the polytropic index. So for instance, for the polytropic index y equal 1, the solution theta is 0 between psi equals 2 and equals 3. The same is true for polytropic index 1, 3/2 and 3, and it's also just marginally at a finite radius, or in other words, for polytropic indices smaller than 5, we have a finite zero of the function theta. So this is interpreted as the radius of the star, or the radius of the stellar model. The first zero of this function, because we cannot interpret negative values of the function theta, we cannot interpret negative densities. So as long as theta is positive in this solution, then we can interpret this as the star, the structure of the star, and the first zero in this picture will be the radius of the star in terms of the normalized radius or radial variable psi. Okay, once the polytropic index is bigger than 5, then bigger or equal to 5, then the stellar model will extend to infinity. So these are the simplest stellar models we can think of these are obtained simply by the polytropic connection between pressure and density. Okay, so the first zero of this, the solution of theta in terms of the solution of the Lane-Emden equation, first zero denoted by psi1 as a function of n, will be interpreted as the stellar boundary for polytropic indices smaller than 5. Okay, now we can calculate from the solution, we might calculate the mass simply by integrating the mass over, by integrating the density over the volume. And once we do it and use the normalizations of radius in terms of alpha, once we use the normalization of the density in terms of the central densities, we end up with the following integral. So this is alpha cubed times 4 pi times the central density times the integral now in terms of the normalized quantities. This is the integral from 0 to the first 0 in terms of the variable psi times the density theta to pi n, and r squared times psi. Now if we can write this integral simply by the Landen equation that's here. So we multiply the equation minus times psi squared. When we integrate times derivative of the integral over psi squared theta to the power n d simply the value of psi squared theta by psi. So we don't need to integrate using the Lane-Emden equation. This is simply, this integral is given by the center, it's the quantity psi squared times the derivative of theta psi at position 0. At position 0, psi is 0, so it vanishes, and the integral of this quantity has to be taken at the first 0 of the function theta, so this has to be minus at 0, it's anyway 0. So this is psi1 squared, and psi1 squared is the first 0 of the function and times the derivative of the function at the first 0. So this is a quantity which is dimensionless and which is of order unity. The dependence on physical variables of M is the normalization value, the normalization constant alpha, normalization for radius, and the normalization for the density, for the central density. So we may express it in terms of some dimensional quantity and alpha cubed times 4 pi times the central density. The radius of our star is normalization of the radius times the zero of the solution, the first zero of the solution psi1 of the function psi1 of n. The mean density is simply the mass over the volume of our star, mass over volume of the star, can then be written in terms of, well, the central density. What is left here, if you take the mass, if you express the mass in the way given above, and also the radius, must express radius in terms of alpha, the central density, and also the radius, then you end up with a relation between the mean density and the central density only, and some function or some quantities, the derivative of the solution at the first zero divided by the first zero and the central density. So if we now express both the value of alpha in terms of, so we express first alpha in terms of the mass and the central density, then and secondly we interpret the central density in terms of mass and radius, then we end up with a relation. So we replace simply the central density by mass and radius, and we replace the value of alpha by mass and density, and density again by mass and radius. We get finally a relation between mass and radius for our polytrope. Okay? This is simply some algebra at which we end up with. This relation, which we get finally, contains only the radius and mass. So the central density has been eliminated and the normalization factor alpha has been eliminated. What is left as from the physical constants is the polytropic constant K and the gravitational constant. This comes from here. So alpha contains the polytropic constant. Let's go back here. Alpha contains the polytropic constant and gravity, and this appears again in our relation between radius and mass. Okay, so we have a relation finally between radius and mass containing the polytropic constant containing the constant of gravity times some of the dimensionless functions, including the position of the first zero of the polytrope and the derivative at the first zero of the polytropic solution. Well, if we ignore all that stuff here, these are only constants, they are physical constant, gravitational constant, and the polytropic constant, then we end up with, ignoring all that stuff here, that radius to the power 3 minus n is proportional to the mass to the power 1 minus n. What we end up with is similar to the case we have studied in a much simpler way without solving an equation before. We obtained a mass-radius relation. A mass-radius relation is always obtained if we prescribe a polytropic relation between pressure and density. We have discussed this morning on the basis of a very simple estimate. Once we assume a relation between pressure and density, then an estimate of the hydrostatic equilibrium and mass conservation will end up or will lead to a relation between radius and mass. Here, on a more sophisticated way, on a more detailed calculation for a stellar model, giving the exact structure of the exact stratification of such a model, we have also a relation between, an exact relation between radius and mass, and this relation depends on the polytropic index r to 3 minus n is proportional proportional to the mass to the power 1 minus n. If n is equal to 3, then the dependence on radius drops out. So the mass is then a constant. If n is equal to 3, so then what kind of power law is that? The power law is, the assumption is P is proportional to rho to 1 plus 1 over n, and what we obtain is that the mass is fixed for n equals 3. This would be the case for P proportional to rho to 4/3, and this is the case once we consider relativistically degenerate electrons, for instance. So we recover for the polytropic case. We recover our results from this morning. On the other hand, if n is equal to 1, then we have a fixed radius. Then the radius is independent of the mass m. Moreover, what we can see then is we have dr by dm is bigger than 0, so the radius increases with mass if the polytropic index lies is smaller than 1 or bigger than 3, and once it lies between 1 and 3, then the radius decreases with mass, and this is typical for degenerate stars, in particular for white dwarfs. For white dwarfs, which means the gamma, the adiabatic index is 5/3, and we have which corresponds to 3/2. The radius goes with m to minus 1/3, and we have the radius mass relation of white dwarfs. For n equals 3, the mass is fixed by the value of k. So if you take the exact value here is, or the exact relation is, if n is equal to 3, then you derive, or you can write the mass in terms of the polytropic constants of the unity times the polytropic constant and the term of the gravity. So what you derive, or what you can derive from this relation, is Chandrasekhar's mass in detail. So you get the exact value of Chandrasekhar's mass simply by taking n equals 3, inserting the polytropic constant simply from the equation of state, which is valid for degenerate, non-relativistically degenerate electrons. So inserting this constant and the gravitational constant, we will derive the mass of a relativistically degenerate electron gas. This for the relativistically degenerate electron gas, these constants depend on natural constant, on basic constants only. So Chandrasekhar's mass can be expressed in terms of fundamental constants only. So this is given by a combination, certain combination of fundamental constants. Okay. Well, I should emphasize here that 1 plus 1 over 1 should not be confused with the adiabatic index. The adiabatic index is determined by the equation of state only. So you have an equation of state, and you require that the changes of state are adiabatic. That means the entropy is constant. This defines the gamma adiabatic. This is d log p by d log rho at constant entropy without any reference to a stellar model, whereas the polytropic index might also include the energy transport, so it requires a particular stellar model. So the polytropic index is usually both including energy transport processes and is not related or cannot be determined by thermodynamics only, whereas as the adiabatic index is determined only by the equation of state. So one should keep the separate polytropic index is not necessary. It can be equal to the adiabatic index, but it does not need to be identical with the polytropic index. So 1 plus 1 over n, the polytropic exponent, is usually not equal to the adiabatic exponent. So keep this in mind. You should not confuse it. It can be equal, but it needs not be able to be identical. Okay. Well, we have already discussed the solutions of the Lane-Anden equation, and then why did we do it? We considered these stellar models because for some cases we will refer to these models and take these stellar models as examples for stellar models, and we will look for their stability properties and their pulsation properties as an example. Even if this is not in general not a realistic stellar model, we may use it to demonstrate certain properties of a pulsating star, which is based on a polytropic model. Just for preparing an idealized model to be discussed later on for its pulsation properties and its stability properties. A particular model which is very, very simple and which is completely unrealistic, but it allows for an analytical, it will show that it allows for an analytical treatment even of the pulsation equation, is the polytrope of index n equals 0. I will show here the properties of this polytrope of index n equals 0. So what does n equals 0 mean? Well, in this formulation, it's a singular formulation. You have to rewrite it in terms as density as a function of pressure, and then you will see it is simply the pressure is polytrope of index n equal to 0 is a so-called homogeneous model, which means the density is constant. It does not mean, again, we have to distinguish between incompressible and inhomogeneous or homogeneous. Homogeneous means that the density is constant with respect to spatial dependence. Compressibility means that the divergence, once we compress our star, is 0. Divergence of the velocity is 0. This does not mean that the stellar model is homogeneous and vice versa. Incompressible means if we compress our star, that the divergence of the velocity is 0, or that the density doesn't change when we compress it. Homogeneous model means that the density is constant with respect to spatial variables. So the gradient of the density is equal to 0 means homogeneous model. So it's certainly a very, very, very crude stellar model, but because the pulsation properties or the pulsations of a polytrope of index n equals 0 allows for an analytical representation both of the spectrum of P modes and G modes and even of the Feynman F mode. Therefore, I would like to discuss this model because you can have an analytical representation of the entire spectrum, which is not possible for other stellar models. So this is the simplest stellar model, but it has the advantage that you can write down finally the spectrum in a closed form. Well, if you have a constant density, the mass is given by density times volume. The mass inside volume of radius r is simply density, which is constant, multiplied by the volume of sphere of r. Then the pressure gradient is given, density is constant, 1 over rho, the p by dr is given by the gravity. Gravity is GMR. MR is given by this function which goes like R cubed over R squared. So the pressure gradient is minus 4 pi third times rho squared. The MR contains another density times the gravitational constant times R. So the pressure is a linear function, the pressure gradient is a linear function of the radius, and we can easily integrate the pressure by simply taking the integral over this function, so that the integral goes with R squared half. Now we have the boundary condition, or the condition we're looking for the value that the pressure vanishes. It's a typical Lane-Emden solution, which is also valid for the polytropic index n equal to 0. So this gives the integral, which is pressure once we denote the outer radius of our polytrope of index n equals 0 by capital R, and we have a quadratic equation, or we have a quadratic solution in terms of the dependence of pressure on radius. Then we have that the pressure is given by 1 minus the relative radius, 1 minus R over the radius of our stellar model squared, times the central pressure. And the central pressure is given by the density of our polytrope times the gravity, essentially. Okay, so this is the solution, the mass mr, and this is the solution of the pressure as a function of radius. It's a quadratic function, so the pressure looks like that. Pressure is a parabola, and it has a 0 at radius r, and this here is the central pressure, which is simply the maximum of the pressure curve. Well, we have already discussed it basically in terms of, you see here, this is the parabola for n equal to 0 here in terms now of this variable xi. Or you can take it, of course, formulate it in terms of the ratio of the radius and the of the radial variable and the radius of our object. Now, what about the stability, or the stability with respect to convective motion? May I remind you, there was this quantity Q, which denotes, or which involves the criterion of stability. Q was given by, perhaps you remember, what was the criterion for the onset of convective instability or stability? Do we remind? This was not the complete criterion. The complete criterion would involve both the pressure gradient and the density gradient. Pardon? Okay, this Q involves the density gradient, the rho by dr, minus 1 over gamma adiabatic times 1 over p, the p by dr. This was the quantity whose sign indicates stability or instability. Well, the rho by dr is 0 for this element, so the value of Q only depends on the pressure gradient. The pressure gradient is, of course, negative, so Q is positive, and once you go back to our criterion, then positive values of Q actually should be 1 over rho times the rho by dr. Bigger than 0 means the stratification is convectively unstable. That's what's the result of our consideration of the stability of our stratification. So the quantity, a combination of density gradient and pressure gradient, that has led to the stability criterion, and for positive values of Q we have instability, and this means what does it mean? Our polytrope of index n equals 0 is a convectively unstable situation. So we conclude, or we expect, that once we perform a stability analysis for the polytrope n equals 0, we will end up with a convectively unstable configuration. It's automatically convectively stable because it only contains the pressure gradient, because due to the homogeneity requirement, the density gradient is 0. So the polytrope of index n equals 0 is convectively unstable. Okay, well, you can see even another property here. Well, once you take out the 1 over rho here, this is 1 over rho times the rho by the r minus 1 over gamma adiabatic p over rho times the p by the r greater than 0. Well, this quantity here, p over rho times gamma adiabatic, 1 over rho over p. P over rho is simply the velocity of sound, is the sound speed squared, gamma times p over rho. So this is 1 over sound speed squared. You see, the adiabatic gamma does not need to be identical to the polytropic index. Here we have discussed polytropic index n equals 0, which means we consider a homogeneous configuration. But once we consider the stability, the criterion for stability or instability, it contains the sound speed, and the sound speed again contains the adiabatic index, the adiabatic exponent. This refers to the changes of state once we take a homogeneous model and we try to compress it or decompress it. Then it follows, the pressure follows an adiabatic relation once the thermal time, once the changes of state are fast enough to guarantee an adiabatic change of state. So keep these two separate. The polytropic index is different in general from the adiabatic index. Okay, that closes, or by this chapter we finish with our digression to stellar evolution, and we turn back to considering our stellar pulsations. Some questions, please ask if there is something unclear, or you disagree, or you object. Please. No comments. So we need to switch now to the file radial linear. So this is not a radial linear. Okay. Yes.
You mentioned that the thermodynamics is being captured that everything is on all the three cases you mentioned. One intermediate which is the other one was
Yes.
the next one was even the convective stars. How means the thermodynamics in case of degeneracy? How do we interpret that?
Well, in the case of degeneracy, the pressure is automatically a function of density only. There is no thermodynamics in the degenerate star. We have no. Well, the energy transport is not covered by. Well, there is actually energy transport, but the energy transport within the degenerate star will occur through conduction. And then we have to go, if we want to consider energy transport in a degenerate star, then we would have to consider the ions. And the electrons, the ions determine some kind of ion temperature, and the transport is given then by conduction by the electrons. So we exclude the thermodynamics. The thermodynamics does not play a role for the mechanical structure, for the equilibrium, because the pressure is made up only by the degeneracy pressure of the electrons. in that sense, you can separate the mechanical equations and the equations for energy transport and the equation. Well, there's not much energy transport going on anymore. What happens is at most at the surface of the white dwarf, or so we may have some energy transport and we may have some radiation which is emitted from the surface, but energy transport does not play a role anymore in degenerate objects.
So can we say that in these cases, of the three cases, there is thermodynamics plays a role, but it is not deciding the structure of our star. Like in some cases, thermodynamics is deciding in some way our structure of the star. In all these cases, which we
well, for the degenerate electron gas, it's simply that the equation of state itself loses one of the variables, so there is no temperature or entropy occurring anymore. In the other cases, we have both the transport mechanism, the energy transport mechanism. For instance, if it's very efficient, then we have constant temperature. So there is still the temperature, still a parameter of the system, but the transport is very efficient and it reduces or it maintains a constant temperature. If we then add an equation of state with constant temperature, then we have formally a relation between pressure and density. And the same is true for Hayashi line objects. Then we have energy transport by convection, and this enforces that we have that the stratification is given by nabla adiabatic, because then the convection is adiabatic, and it reduces or it ensures that we have an adiabatic or a constant entropy structure. Then we have, well, first of all, the transport mechanism requires the entropy to be constant. Then, additionally, the constant entropy means that the entropy drops out of the equation of state, and the pressure is only a function of one additional parameter, which can be chosen to be the density. So there are several thermodynamic processes included or combined to provide a polytropic relation between pressure and density. Does it answer your question? Any other question? Okay, so let us continue now, and let's come back to the study of stellar pulsations. And first of all, we will consider spherically symmetric pulsations. So we will consider perturbations which do not violate the spherical symmetry of the star. So to say, the stellar evolution model is usually done in terms of spherical symmetry, and we will assume that our perturbations, our pulsations, will also be spherically symmetric. Okay, well, stellar evolution was characterized by hydrostatic equilibrium, by acceleration being equal to zero, and it is governed by the remaining two timescales, which is the thermal timescale and the nuclear timescale. On the contrary, or in contrast to the stellar evolution, the pulsations are characterized by deviations from hydrostatic equilibrium. So we must take into account the acceleration. The acceleration is no longer zero. The pulsations operate on the dynamic of timescale. So this is the important point. It's the opposite of the stellar evolution. However, these pulsations occur on a timescale which is much shorter than the nuclear and the thermal timescale. So nuclear changes, for instance, of the composition will be disregarded, and also the nuclear processes will be disregarded for considering pulsations. So chemical composition is kept constant because the time needed to change chemical composition is on the nuclear timescale, and we will disregard it or keep the nuclear change of composition constant. Well, this means that the pulsations will be governed by the dynamical and by the thermal timescale. In the ideal case, or in an ideal case, we can even disregard the thermal timescale if the pulsational timescale being of the order of at most a few hundred days is still much longer than the Kelvin-Helmholtz or the thermal timescale, which is of the order of 10 to 7 days, 10 to 7 years. So one may even think, if one compares the global thermal timescale, with the dynamical timescale, that we can disregard thermal processes and disregard the derivatives with respect to time which operate on the thermal timescale. Actually, it's not true. You cannot completely disregard it. You have to go more into the details. So there's one approximation to the problem where we can disregard the time change of the entropy, the place where the derivative with respect to time according to the thermal timescale appears is the derivative of the entropy with respect to time. Well, we'll come to that in more detail. Well, we have to take into account, for certain stellar models, we have to take into account the thermal timescale and the time derivative of the time derivative of the entropy. Okay, that's what is needed to be said about the timescales. Well, for the strategy which we will follow to consider radial stellar pulsations, let us motivate the strategy a little bit by the observations. Well, once we observe pulsating stars, then we recognize that most of the pulsating stars maintain their mean properties. So they will have a mean effective temperature, they will have a mean luminosity, and so on. So while the stars are pulsating, they are pulsating around a mean value concerning for instance, the radius will be changed. It oscillates or varies around a mean value, and it oscillates around the mean temperature and the mean luminosity. And in most cases, these changes or the variation of these quantities with respect to the mean value is small. So if we consider the luminosity, for instance, the luminosity will for Cepheids will be of the luminosity change, the luminosity brightness is usually less than 0.1 magnitude, whereas the magnitude or the magnitude which corresponds to the total luminosity of the star is of, say, third or fourth magnitude. So the mean luminosity is much bigger than the variation of the luminosity. That's true for the other quantities too. So the pulsations may be regarded as a superposition of this variation on top of the mean quantities of the mean properties of a hydrostatic star. That means also, or does also imply that these pulsations may be described as small time-dependent perturbations of a time-independent stellar model. So we have a hydrostatic time-independent model, and superimposed on this star are the pulsations or the perturbations of the star, which are time-dependent, and they seem, from the observational point of view, they seem to be small compared to their mean values. Okay, we take this as a motivation for constructing a model or constructing a strategy or performing a strategy how we shall describe these pulsations which are superimposed on a hydrostatic stellar model. Okay, so what we do first, we need to construct a stellar model which has or maintains the mean properties. So we need to construct a stellar hydrostatic model of some object which we want to study. That means either we perform stellar evolution calculation and or tune these calculations in such a way that we meet the observed parameters of the star. So we do stellar evolution calculations. For instance, we observe some star in the HR diagram. Take a star in the HR diagram. Luminosity as a function of effective temperature, T effective log L. Well, then we start off from this should denote the main sequence. We start off from the main sequence, hydrogen burning, contraction phase, and then the star goes to the right into the domain of red giants. Well, suppose the observed position of our star is here somewhere. Well, then we start here. This track will depend on mass. So the parameter of, well, if you have a higher mass, then it looks like that. So the mass of this track is higher than this. Well, to meet the observed position, we may have to tune the star. So in that case, the mass is too small. In that case, the mass is too big. So we have to fine-tune until we find a track which meets the position of our star. Then we will have an object, or we will have a model here which is close to the observed position of our star. We have the mass of the star in that case, and we meet it at the observed position in terms of effective temperature and luminosity. Okay, this is one way to generate stellar models which match the observed positions and which will give us a hydrostatic stellar model which we can test or investigate for stability and pulsations. The other way would be we adopt the observed parameters once we do not have a stellar evolution tracks available. We adopt the observed position in terms of luminosity and effective temperature, and in most cases the mass is the parameter which is not very well known. Maybe we have an estimate for the mass, or we consider simply a range of masses, and we can and hopefully, or we may hope then that the actual mass of the object will lie in the range of masses investigated. Of course, also from observation of the star, we may derive the chemical composition, which is necessary to choose the right opacity tables. If we do that, then we can construct an envelope model. That an envelope model is obtained by integrating not the full system of equation, but the system of mass conservation, of hydrostatic equilibrium, and of energy transport. Well, that is, so we assume these four, or we assume the observed position, take an estimate for the mass. This is the least well-known property, and we adopt the observed chemical composition. Then we can construct an envelope model by solving the following three equations. Well, this is the first equation is the definition of the mass coordinate, or if you like, the mass conservation. The second one is the hydrostatic equilibrium, and the third one is the energy transport. Well, in case of convection, we have to reformulate this equation, and we have to take the formulation in terms of nabla relating the temperature gradient to the pressure gradient. Okay. Well, this equation, the advantage of this envelope model calculation is that we can perform then an initial value integration by integrating these three equations from the photosphere inside to some maximum temperature which might be defined or can be chosen just as to avoid for instance, nuclear reaction, because what we do not integrate here is the equation for luminosity. The L by the M is not integrated because we assume that in the envelope there are no nuclear processes. What we do exclude in an envelope integration is we exclude the nuclear active regions, the core of the star. That means if we exclude that, then the luminosity is constant. Well, dl, the equation which we should integrate is dl by the m is epsilon. If epsilon, the nuclear energy generation, is disregarded, then dl by the m is 0 and l is constant. So we don't need to integrate this equation, but we keep what we consider constant luminosity, namely the constant luminosity as observed for the object. Okay, constant chemical composition, nuclear energy generation is 0 and therefore the luminosity is constant and equal to the observed value. Then using the usual boundary conditions at the photosphere, we can now integrate these three equations inward. We start with mr equals to m. We know the mass. This means we have the value of m and start with the independent variable mr equals to m. We start with the effective temperature. Effective temperature is given. Then the radius will be obtained from Stefan Boltzmann's law. We have the temperature, luminosity, then we have the radius, and we have an additional condition which is identical, initial condition which is identical to the conditions usually used in stellar evolution theory, which determines the pressure at the photosphere in terms of the gravity. This is a prescription obtained by considering an estimate of the stellar atmosphere. Okay, so we don't solve, this is the advantage, we don't solve a boundary value problem, we can solve an initial value problem, which is much easier than to solve a boundary value problem. Integrating from the photosphere inward, integrating these equations and providing the pressure stratification, the temperature stratification, density stratification, and so on through an initial value integration. So the first step in any case or in any investigation of stellar pulsations and stability would be the construction of a hydrostatic model, either obtained by envelope integration, by envelope model, or if we are able to do this, we perform stellar evolution calculations for the parameters and try to match an evolutionary track which goes through the observed position. So the first step will be the construction of hydrostatic stellar model, either by stellar evolution calculations or by envelope integration. Okay, shall I stop here? Okay. So thank you for today, and tomorrow we will then consider the next steps we will perform to calculate and to describe stellar pulsations and stability.